Hello everyone. Welcome to our introductory video to slope deflection method of analysis. In this video, we are going to talk basic introduction to slope deflection method of analysis. So we had previously talked about constant deformation method. In this video, we are going to talk about slope deflection method of analysis. So we are going to solve both the beams and frames by using this method of analysis. On the frame, we have sway and non-sway as well. We'll be talking in detail about sway and non-sway frame in further lecture series. So right now, let's talk about in a basic. We'll be doing problem in our next lecture series, but it is very important to understand the basics in order to go on for our problems. So this method is suitable for analysis of both the beams and residual data frames. In this method, basic unknowns like slope and deflections can be calculated. So we basically know what slope is. So if this is a beam, let's say we have deflection in sorts of way, and if we measure deflection, this is a, let's say theta a with respect to b, point theta ab. So fully you have seen others similar videos of my related to structure. You can see my constant introduction to constant deformation method in order to learn the basics about rotations, slopes and deflections. So let me just explain to you in brief, so hopefully you have understood about that. So slope and deflections, we can calculate the basic unknowns like slope and deflection. A moment at the end of a member is first written in terms of unknown slope and deflection of end joints. So in order to solve by using slope deflection method of analysis, we are going to write the moment at the end of a member. So moment at the end of member, let's say MAB, it will be written in terms of slopes and deflections. So utilizing this, will be finding out our unknown moment. So how we'll calculate that, I'll tell you in the further part of the video. So considering a joint equilibrium equation or set of equations are formed, and solution of these simultaneous equations give unknown slope and deflection. So this will be more clear when we go into our problem one. Then end moments of individual members are determined. Okay, so such as simple assumptions, simple terms which we'll get to know after we solve our problem 1, problem 2 assumptions. So there are some basic assumptions as well. All the joints are rigid, that is the angle between any two members in a joint does not change even after deformation. So let's say some kind of deformation happens. So as you can see, we have a member A, we have member A, B and C. So let's say they are maintaining certain angle theta. So let's say some due to some external forces, some moments, some kind of angle is some kind of deformation is caused in them, and as a result, let's say the beam differs in. So let's say the member AB, this is the original position, and it changes into this position A B. So despite this, the angle theta, it will remain same, and our uh, this is our member BC, it will get deflected in this position as well. This is A dash, this is our original AB. So despite deformation, the angle between two members will always remain same. This is our first basic assumption. So our second basic assumption is distortions due to axial deformations are neglected. So due to axial deformations, so let's say some kind of axial forces, or due to some reactions, axial deformations might form in this way. But this type of axial deformations are neglected. Shear deformations are also neglected. These are just basic assumptions, so we don't need to focus much more on them. So what's important is sign conventions. Sign conventions are really important. So sign conventions will be really important. So moments, so clockwise end moments, so clockwise end moments will be taken as positive, while anti-clockwise end moments are taken as negative. End moments means the MAB. So let's say I have MAB, this is going to be moment at AB. I might have another um joint over here, let's say C. Should be a member AC, member AB. So this will be my end moment, will be at the end section of a member. So clockwise end moments, this refers to the clockwise end moments MAC. So this is acting in anti-clockwise direction, so it's going to be negative MAC. Similar rotations, clockwise rotations. So let's say I have a beam and let's say it gets rotated in such a way that it produces theta a b. So this is my rotation at a with respect to b. This is in clockwise direction, so it will be taken as positive. Meanwhile, anti-clockwise rotations will be taken as negative. Anti-clockwise rotations will be taken as negative. Settlement delta is positive. Settlement is generated by delta, as rotation is generated by theta. Settlement delta is positive if right side support is below left side support. So if right side support is below left side support, delta is negative. So this will be much more clearer by our example. So let's see, we have a certain example of a beam over here, and we have such a case scenario such that b has deflected downward to position b dash. We have our deflection b. So for our we have our two sections, section ABB and section BC. So for our section AB, if we are looking for our section AB, this delta will be taken as positive. While why? Because right side support, because the right side support is below left side support. So left side support is upward with respect to right side support. In this case scenario, we'll be taking as deflection as positive. So this is written over same over here. Settlement is positive if right side support is below left side support, or left side support is so you can assume in this way. I have assumed this simply by my hand. So if my left hand is above my right hand, left hand is above with respect to if left hand is above with respect to right hand, in that case scenario, if left hand is above, it is going to be positive. But meanwhile, if right hand is upward, right side or right side right support is upward, it is going to be negative. So remember, in such a way you can make such mnemonics. So while for meanwhile for beam BC, delta is negative. Why delta is negative? Because for beam BC, the left side support is downward while the right side support is upward. So if my right hand is up, settlement is negative. Right hand or right side support is upward, settlement will be settlement will be taken as negative. So you can simply use simple mnemonics. If left hand is up, positive. If right hand is up, negative. So now we have our derivation of slope deflection equation. So we'll have a certain formula that will work with in slope deflection equation. This is my original shape of the beam. We have point load A and B. I have two roller supports A and B. So let AB be a member of the rigid structure. Figure shows deformed shape. So there are due to whenever some load is applied at a beam, different kinds of displacements will take place, namely rotations and displacement. So in this part, we'll be mainly talking about rotations. We'll be talking about our rotations, and we'll be talking about our settlements, especially you can say deflections as well, or settlements as well. Let me write rotations and okay, let's use the word settlements only. Rotations and settlements. So as you can see over here, due to the point load W1 and W2 in this beam, as you can see, there is moments being applied. Moment at A with respect to B, we have a moment at B with respect to A. Similarly, we have rotations as well, we have deflections as well. So we'll be writing this. So what will be in this deformed sum of the beam, we have our end moments and we have our deflections. So we will be calculating this end moments and deflections, but we will express these end moments and deflections in terms of rotations and settlements. So final moment at end A and B are written as MAB and MBA respectively. So due to given loadings and moments, despite this final moments, there will be end moments as well, which are written as. So we have our final moments. This is one thing. Next we will have our end moments as well. So these end moments are now will are denoted by MFAB. Why they are written? Because this is since these moments are similar to end moments in fixed beams. So what I haven't said yet is in slope deflection method will be taking the beams as fixed end beams. So we will be taking them as fixed end beams. Whatever may be the type of support in the beam, roller, hinge, we don't care. We will suppose the beam as fixed in beams and determine those deflections, moments, etc. So what we have is we'll have firstly um, we will have fixed end moments. So we have fixed end moments at A is written as MFAB, while fixed end moment at B is written as MFBA. So firstly, B refers to the position where the moments are being created. So these are called as fixed end moments. Fixed end moments. So similarly, settlement also takes place without any rotations of the end. This is similar to settlement of supports in a fixed end beam. So from our analysis of fixed end beams, the end moments developed due to settlement are 6 EI del by L square. So the end moments which will be developed, as I said before, MAB and MBA, there will be a fixed end moment developed due to this settlement. So the settlement delta which is given by the formula 6 EI del by L square. This all will be used in our main formula. Similarly, moment M dash AB comes into play in similar support to cause end rotations theta A1 and so cos theta A1 and theta b1 at A and B. Similarly, moment MBA comes into play so we can just simply read this, and we'll have our first rotations theta A1 will be writing this rotation in terms of our moment, in terms of our moment MABL divided by 3EI. So for this theta A1, this will be MAB into the L divided by 3 EI. Similarly, we have our theta B1. For theta B1, there will be difference. We'll be using 6. Similarly, theta A2 will be since this time we have our end moment at B. We'll be writing this moment MBA into L divided by 6 EI. Similarly, for theta B2, it will be MBAL divided by 3 EI. So this 3 and 6 refers to where the end moments are acting and at what place where at what which rotation we are calculating with reference to at what position those moments at with reference to those positions where those moments are active. So this is really simple, so you don't need this derivation much, so I'm just explaining. So theta A will be theta A1 minus theta A2. So it's simple. We get this theta B as well. So this is simple. So we'll be multiplying theta a by 2 and we'll add equation 1 and equation 2 to get this relation, which is going to be really important because this refers to our end moment AB. So this will be equal to 2 EI divided by L 2 theta A plus theta B. So I explained before, we'll be writing our end moments. We'll be writing our end moments we'll be writing our end moments in terms of rotations and deflections. So firstly, for our moment MAB, we have successfully written this formula in terms of rotation. Similarly, MBA will also be equal to 2EIL divided by theta A plus 2 theta B. So final moments at end A, MAB is given as, so as I've explained before, the final moment will be the summation of fixed end moment, which I've explained before, which is caused due to this which will be caused at our end. Similarly, then we have our 6 EI del by L square, which is called settlement, plus MAB, which is our end moments. We have got our value of MAB to be 2 EIL to theta A plus theta B. So on arranging this, we get, this is going to be very important. So this is the main formula with reference to which we'll be completing our slope deflection method, which will be moment AB, MAB is equal to fixed end moment AB plus 2EAL plus 2 theta A plus 2 theta B, 2 theta A plus theta B minus 3 del by L. Del refers to settlement. Similarly, MBA will be fixed end moment. Instead of AB, we'll have BA. So plus 2EI by L theta A plus 2 theta B minus 3 delta by L. So there will be the difference of this parameter 2. So equation 1 and 2 are called as our slope deflection equation. So this is our basic derivation and how slope deflection equation is derived and how it is explained, how it is expressed in terms of rotations and deflection. So this derivation is not much of use, so we'll be using what will be using this formula highly in our problems. So fixed end once we have calculated, we have used our term fixed end moment and FBA. So this fixed end moments will be different. This fixed end moment will be different depending upon the loading condition. So there are various case scenarios, so we'll be talking about them one by one. So we have our first case scenario. So as I explained before, we will be taking our whatever type may be the support of the beam, may it be roller, hinge, maybe fixed. We will be so let's say we have one example. So W. So for this beam, in order to solve by fixed and in order to solve by slope deflection method, what we will do is we will be taking this beam as fixed end beams, and we will calculate our fixed end moment. So in this case scenario, when our unit load W is acting at equidistance L by 2 and L by 2 from both of our ends, the fixed end moment at A will be fixed end moment AB will be WL by 8. Similarly, fixed end moment BA will be uh, fixed end moment B A will be WL by 8. This sign will be positive, this sign will be negative because this is clockwise moment versus anti-clockwise moment. Similarly, if the point load is not acting equidistance, let's say it is acting at distance A from B and distance A from one side and distance B, and that case it will be WA B square divided by L square WBA square by L square. So fixed end moment AB will be minus WAB square by L square, while fixed end moment BA will be WBA square divided by L square. So you need to remember all this formula. Similarly, for when UDL is acting along the beam, it will be WL squared by 2 bit WL squared by 2 bit. But if the UDL uniform distributed load is acting at shortest span A, the fixed end moment AB will be WA square divided by 2 by L square 6L square minus 8AL plus 3 square, while BA will be WA cube divided by L square 12 minus 3. But let's say instead of load of a moment was acting at a distance from the end from point A, in that this is point A, this is point B, then our fixed end moment AB will be written as MBL square B minus 2A. This will be negative. Similarly, fixed end moment BA will be MA divided by 2B minus A. Similarly, for our UBL will be WL square by 20, WL square by 30. Similarly, if we have this type of loading structure, so it's not exactly a UVL, but this is a type of UVL. We have 5WL square by 96, 5WL square by 96, but this is at this is distributed over 5 L by 2. So this will be much more clearer when we will be going into our problems. So this is our problem one, where we will be going for a two-span continuous beam. So what you need to understand is this our main formula. In this main formula we have fixed end moment MFAB. So from this video, what you need to, the theme of this video is the this will be the formula which we'll be working on, and in this formula we have one important equation which is MFAB, which is the fixed end moment AB, and this will be different for different case scenarios. So we have different case scenarios. So what we can do is we can copy down all these formula. You need to copy down this formula and this formula, and you need to copy down all these fixed end moments formula for different case scenario, and after doing this we can easily go on to our problems. So hopefully this video was of help to you. So if you like our video, do subscribe the channel and share with your friends. Thank you.